Colab environment. So click on this file. And here we are in our project 3. Now for project 3, I need NumPy. I will import NumPy as NP. I need logistic regression. So I will import logistic regression from sk.learn_model. I need Gaussian Naïve Bayes classifier. So I will import it from sklearn.naïve Bayes. I also need a train test split function, which I will import from sklearn.model_selection. I need matplotlib and I need pandas. So let's run this cell to import all these necessary Python libraries. Now it's time to import the data. So I am going to use the Titanic train dataset. We have already used this dataset in our sections on KNN and logistic regression. Okay, so this dataset is present inside my folder. So in order to read this dataset, I need to mount the drive. Let's mount the drive here and see how long will it take. So it is asking for the permission. Whenever we try to mount the drive, it asks for permission. So we have to permit Google so that we can easily mount the drive. So here you can see that the drive is being mounted, and after a few seconds it will be mounted, and then we will be able to read the data. Now you can see that the drive has been mounted, and we can refresh from here and we can see that there is a drive here. So click on the drive. Inside the drive, I have a my drive. Click on my drive. Here is my course material. So inside the course material, I have supervised machine learning. Inside a supervised machine learning, I have here Bayes Theorem and Naïve Bayes Classifier. So inside this, I have this Titanic train.csv dataset. Therefore, I need to copy the path from here so that I can import the dataset easily. So here we have 3 vertical dot. Click on that. Here is the copy path. Click on that, and now I add a cell here and I will copy the path. Okay, so let's run this cell. The path has been copied, and now it's time to import the data. So this data is in terms of CSV file. So we have to use pandas in order to read this CSV file. So command is pd.read_CSV. Let's run this cell. So we can see that we have successfully imported our data set, and this is the shape of the data set, that it has 891 samples in total and it has 12 columns. Let's see the head of the data set. And we can see that these are the first 5 samples of the dataset. We have the features like passenger ID, passenger class. This survived we will use as a target value or label. So this survived has 2 values, 0 and 1. 0 means the passenger did not survive, and 1 means the passenger survived after the Titanic accident. Okay, this is the column for the name of the passenger, the sex of the passenger, the age of the passenger. This column is about the sibling and the spouse which were traveling with the passenger, and this column is about the parents and children which were along with the passenger. So this is the ticket number, this is the fare, this is the cabin, and this is embarked. So embarked implies where the traveler mounted from. So there are 3 possible values for the embark in this dataset, that is Southampton, Cherbourg, and Queenstown. So these are the 3 places from which the traveler mounted on the Titanic. Okay, so these are quite a few number of columns, like to be exact, these are 12 number of columns. Now check the passenger died. Take the number of passengers which died in the accident. Passenger. Okay, so this is our column which tell us which of the passenger died and which of the passenger survived. Okay, so in order to read this column, so name of my data is train. We can see here the name of our data is train, and this is one of the column of this data set. So in order to read this column, I have to write the command train survived dot value counts. Let's run this cell. Now the value counts will tell us about the number of zeros and number of 1 in that column. So we have 549 passengers who died and 342 passengers who survived. Okay, now it's time to drop the irrelevant feature. So the passenger ID, name, ticket, and cabin. If we go back and see these column, we have passenger ID, name, ticket, and cabin. So these are the irrelevant features. They do not provide any information about the labels. So let's drop these features permanently. So the command is train.drop. These are the features: passenger ID, name, ticket, cabin. These are our column. That's why axis is equals to 1. In place is equals to true because we want to remove them permanently. So let's run this cell and we can see that these features have been dropped or removed from our data set. Now check for null values. Is there any null value in any of the column? So we are checking for null values. So the command is train.isNull any, that is there any null value? So we can see that there are null value in the age column and there is the null value in the embarked column. Now we will deal both of the columns separately because embarked is the categorical column and age is the column which has numerical values like 22, 38, 26, and this is our categorical features like Southampton, Cherbourg or Queenstown. Okay, so we will deal them separately. So what we do with the age column? So we will calculate the mean of this column. Here we have calculated the mean. Train age, here I am reading the column age. Here I am calculating the mean of the column and I am replacing. Fill means filling null values. So I am filling the null value of this column with the mean of the column and I want to make it a permanent change, that is in place is equals to true. So let's run this cell and now check the null values again. So we can see that in the age column there is no more null value and we have dealt with the age column. So we have replaced the null value in the age column with the help of the mean value of that column. Okay, now what we are going to do with embarked. So basically it is the categorical feature, this embarked. So we are going to replace the null values. That is, if there is any null values, we are going to drop basically the null values. If there is any null value, we are going to drop that sample or that row from our data set. So drop train.drop NA, it means train is our data set. Drop NA means dropping null value and we want to drop them permanently. Therefore, in place is equals to true. So let's run this cell and now drop the rows containing the null values. We have already done that. Now it's time to check the null value. So we can see that there is no more null value here. And now we can see our training data. And now this is our training data. This is our survived column, which we will use as a label. Now this is passenger class, this is sex, this is age, this is sibling and spouse, and this is about the parent and children. This is fare and this is embarked. So we can see that we have quite a few numbers of features now. Now the sex column and the embarked column or the sex feature or embarked feature, they are categorical. They are male and female, and here we have S, C and Q values. So we remember in the section of data pre-processing where we learn how to deal with the categorical data or categorical features. So we have to create the dummy variables, and after creating the dummy variables, we have to drop the first column for the dummy variables of each categorical data so that we can avoid multicollinearity or the repetition or the redundancy of the feature. Okay, here we are creating the dummy variable. So the function is pd.getDummies. And I am going to create the dummy variable for the sex column first because it is the categorical column, and drop first is equals to true. That is, after creating the dummy variables, we will have two columns, that is male and female. So in that case, we will drop the first column. Okay, let's run this cell. And here I am also creating the dummy variables for the categorical feature embarked. And I am doing the same. That is, after creating the dummy variable, I am going to drop the first column. Okay, let's run this cell. Now it's time to adding those dummy variables which we have created here to our original data. So basically we are going to perform the concatenation. We are going to add this dummy variable with the columns of originally present data set. So we are going to use pd.concat. This concat is the short form of concatenation. So we are going to perform the concatenation of the columns, and the concatenation is between the train, which is our data set, this data set train, and the sex column and the embarked column after creating the dummy variable. So let's run this cell to perform the concatenation and observe our new form of the data. So we can see that after concatenating, if we see at the end, we have a male column, we have a Q column which represent Queenstown, and we have S column which represent Southampton. So in place of embarked, we have Q and S, these two dummy variables, and in place of sex, we have a male dummy variable. Now, since the dummy variables have been created for sex and embarked, so it's time to remove those columns. So we are removing sex and embarked because their dummy variables are created. So we are going to drop sex and embarked. So these are the column. That's why axis is equals to 1. In place is equals to true means we are going to make it a permanent change. Let's run this cell. And now we can see that there are no more categorical features, and we have created the dummy variables for the categorical feature. So this is the final and clean form of our data set. And now it's time to extract features and labels so that we can perform the classification. If we see that there are quite a few columns like sibling spouse column, which has all the values either 0 or 1. Similarly, male, this Q and S. These are the 4 column where we can see there is a lot of repetition. It means this data is not totally uncorrelated. There are a relationship, there is a correlation between those features, especially whose values are 0 and 1. And we know from project 2 that if the data is correlated, if there is a correlation between the data, in that case, if we compare the performance of Naïve Bayes classifier with the logistic regression, then logistic regression perform well if there is correlation in the data. Okay, so first step is to extract the features and labels. So everything except this column which is survived is our feature. So in order to extract the feature matrix, we will drop only that column and we will retain all the rest of the columns. Let's run this cell to find the feature matrix. And these are our labels, that is our y values. So y is equals to train survived dot values. Okay, so we have extracted x, we have extracted y. Now it's time to perform a train test split. So here is my function train underscore test underscore split, which is going to perform the train test split. So the first input is a feature matrix, then the labels, then the testing size. So here the testing size is 20%. That is, I am going to use 20% of my data in a test and remaining 80% data as a training. Okay, so the random state is equals to 42. So this random state ensure that every time I run this cell, I will get the same samples in the training component, testing component, in the labels, that is training label and the testing label. Let's run this cell to perform a train test split. And here is the shape. So we have 178 samples in our testing data. So these are the features. So we have 178 samples in our test data and remaining samples are for the training component. Now it's time to standardize the data. For standardizing, we are importing standard scalar from Scikit-learn preprocessing. Here I am instantiating standard scalar and I am calling this variable as SC. Here I am fitting my standard scalar to the training component, and here I am transforming my testing component to standardize the data. Let's run this cell to standardize both training and testing component. So first we are going to apply a logistic regression, and then we will apply Naïve Bayes classifier in order to perform the comparison. So here I am instantiating logistic regression and I am calling it as a model. Here I am fitting the model to the training component, and basically what I am doing here is I am training my model with this training component. Let's run this cell, and this model is now called LR. Let's get the prediction from LR. Here I am getting the prediction, and here I am calculating the accuracy of the logistic regression model by comparing the predictions of a model with the actual test label. So let's run this cell, and we can see that the accuracy is 77.53%. So the accuracy of logistic regression classifier is 77.53% on this Titanic dataset. Okay, now it's time to apply Naïve Bayes classifier here. Now for Naïve Bayes classification, we have to import Gaussian Naïve Bayes classifier. I am instantiating it and I am calling the variable NB. Here I am fitting my model to the training component. Let's run this cell. And here it's time to get the predictions from the model. And here I am going to calculate the accuracy. And I am going to calculate the accuracy by comparing the predictions of the model with the actual testing label of the data. Let's run this cell, and we can see that here the performance is very, very similar. We can see that the Naïve Bayes performance also created 77% accuracy, and to be exact, it is 77.53. So till now, what we have observed is since logistic regression model and Naïve Bayes classifier or model both are probabilistic model. So both use probabilities in order to perform the classification. So here for this data set, the performance of both model is equal. Okay, let's predict the class probabilities first from the logistic regression, then from the Naïve Bayes. And after getting this, what we can do here, we can make a table where we can see the probabilities and the class prediction. So we have created this table before in project 2 as well. So this is the same line of code. So this is the same code. Here is the table. So here is the predicted class probability of a Naïve Bayes classifier about class 0. Here is the probability about class 1. And here is the class prediction. So we can see that it is 0.95 for the first sample. Therefore, it belongs to class 0. The probability of first sample is high with class 0. That is, it is 0.95 or 95%. Therefore, it is assigning a 0 here. If we see the logistic regression probability for class 0, it is still high. It is also high for a class 0 as compared to class 1. But those values are different because we have learned that one is the generative model and other is the discriminative model. We have learned these models about when we studied a lecture where we compare the logistic regression and the Naïve Bayes classifier. Okay, so we also see that here the probabilities are also different. Here Naïve Bayes is showing that the probability of a sample 2 with class 1 is 1, that is 100%. On the other hand, the logistic regression is saying that it is 96%. So in this way, we can see that their performance is exactly the same. They have predicted the same classes. Okay. Now, the important thing of this project has come. Now we are applying PCA to create uncorrelated features. Now, what is PCA? So student, PCA is principal component analysis. So what is principal component analysis? Okay, principal component analysis is unsupervised machine learning technique which is used to reduce the feature and also to create the uncorrelated or the independent feature. So right now for this project, you don't need to worry much about what is actually the PCA and how it works. We have a complete section on our unsupervised machine learning section of the course. So you will study with this in the detail. You will also do the project on PCA as well. So right now, what you need to understand is that PCA is used to create the uncorrelated feature, and it is also used to reduce the number of features. So here I am importing PCA from sklearn.decomposition, and I am going to reduce my original data set into 2 components or 2 feature only. Okay, if I go back here where I extract the features, you can see that we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 features. We can also see from here that we have 8 features. Now, when we apply a PCA, what we are going to achieve is that after PCA, we will have only 2 features, first of all, and those features will be independent. So here I am instantiating PCA for 2 components. Here I am fitting the PCA to the training component, and here I am fitting the PCA, or basically I am transforming the testing component, because we know from our section of data preprocessing that fit_transform is only used for the training component. And for testing component, we only use the transform. Let's run this cell to create. And here, if we want to see our components, like if I want to see x_PCA, xPCA_test dot shape. So now we can see that now our shape is 178 by 2. And before PCA, our shape was, testing data shape was 178 by 8. So the number of samples are still same. It is still 178, but now we have reduced 8 features into 2 features. Here. So after PCA, we have only 2 features in our data set. Now check the correlation between the features. This is the same line of code which we have used in project 2 as well. So we are going to check the correlation between the PCA features now. So this is my first PCA feature of a training data, and this is my second PCA feature of a training data. And here is dot round 2. We know that when we write this dot round 2, we will get the value. We will only get the 2 values or 2 digits after the decimal place. Let's run this cell. So we can see that the correlation between feature 1 with itself is 1. With the correlation of feature 2 with itself is 1, that is 100%. But the correlation between feature 1 and 2 and 2 and 1 is 0. So here we have created the correlation, or we have turned our data into independent state using PCA. So we can see that the correlation between feature 1 and feature 2 is 0. So here we have 2 features after PCA and their correlation is 0. So that is the uncorrelated data. Now apply logistic regression on uncorrelated data. So for uncorrelated data, I will use the PCA component of the training and PCA component of the testing. Here I am fitting my logistic regression on a PCA data. Here I am getting the prediction, and here I am getting the accuracy. Now its accuracy is 70.22. If we compare the previous accuracy, it was 77.53. So the accuracy of logistic regression has dropped by 7%. Now the dropping of accuracy is reasonable here. The reason may be that we have reduced 8 features into 2 features. Okay, now when we have reduced 8 features into 2 features, so there is a chance that we have lost some information. So by losing that information, our accuracy of the model has reduced. Let's check the performance of Naïve Bayes on uncorrelated data, that is on a PCA data, where we have lost some information after reducing number of features from 8 to 2. So here I am instantiating the data. Here I am fitting the instantiating the model, and I am calling it np_model_PCA, and here I am fitting my model to the training component of the data. Okay, here I am getting the predictions, and here I am calculating the accuracy. Now we can see that the accuracy of a Naïve Bayes classifier also decreases from 77.53 to 72.47. But this 72.47 accuracy of Naïve Bayes on uncorrelated data is better than the performance of a logistic regression. So we see when we learn in the theory where we compare about the logistic regression and Naïve Bayes classifier, that if the data is independent, this is the one of the important condition to apply Naïve Bayes. So we can see that when the data is independent or uncorrelated, we have created the uncorrelated data from the correlated data using PCA. The performance of Naïve Bayes is better than the logistic regression. And when the data was correlated, their performance was equal. So in this project 3, we compare again the working or the performance of logistic regression classifier with the Naïve Bayes classifier. And we observe that if the data is uncorrelated or independent, which is one of the important condition for Naïve Bayes classifier, in that situation, Naïve Bayes classifier will perform better than the logistic regression classifier. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture.